are folded, and if we will, and somebody put you in front of the tail of elephant or near the leg of elephant, then we will guess, oh, this is a rope or this is a tree. Means what? Depending on the way we speak, depending on the way we look, we speak. So but in 2009, Barack Obama said, when we're talking about a smart grid, as the source figure you can see, it is taken from the smartgrid.ieee.org. So he said that when we're talking about the smart grid, means smarter, and the smarter will become starting from the generation, transmission, and distribution. Previously, in our parents' days, we generally see generation, transmission, and distribution. But here the roles come about the customer participation, operation, market, and service provider. And the overall objective will be what? It means it smart, best, and optimum utilization of all the available resources. And when we're talking about the available resources, we are talking about all conventional and non-conventional resources. So the definition of the smart grid given by National Institute of Standard Technology, they say modernized grid that enable a bidirectional flow of energy and use of two-way communication and control capability that will lead to an array of new functionality and application. We can, in short, we can say, as we are the faculty members and we are teaching in a class, until unless there is a bi-directional flow from faculty to the student and student to the faculty, the efficient and the reliability will, and the output will be less. Because whatever we are throwing in a class, whatever we are presenting in a class, whatever we are speaking in a class, if it is going in a one direction and nothing coming from the direction in the opposite side, then I think the output will be less as compared to the, if there is a two-way communication. So similarly, when we're talking about the smart grid, there will be a bi-directional flow of energy as well as communication and control capability protocols. But what does IEEE says? IEEE says a smart grid is a system of systems. Means it is a system of systems where three layers are there. First layer, the people and the guys, as we are from electrical engineers, and the second layer is the engineers from the communication side, and third layer is the IT, the computer layer. And we can see that two layers, layer number 2 and layer number 3, make the infrastructure more smarter, because there is a communication protocol, there is a software, there is some xyz uh, you know uh, control protocols in softwares, in communication protocols. So these all protocols make our power system, our energy system more smarter infrastructure. So this is our older power system, as we already talk and we teach students कि generation होता है, transmission, then distribution, and then we are the consumers, and the primary transmission, secondary transmission. And when we're talking about the transmission, so these days in India, generally we have 1200 kV transmission line, which was set up by the power grid, and the test plant, which was constructed in Bina, MP, with the cost of around 1200 crores, and the commercial line which was running right now, which is in the Aurangabad to Wardha in Maharashtra. And similarly, when we're talking about the transmission line, which in the DC, HVDC, so the recent development that India has done, again by Power Grid, as Power Grid taking care of all the transmission, it is coming from Tiruchirappalli, Assam to Agra with the capacity of 6,000 megawatt with 800 kV, right? So these are the two achievements that we have recently gained by the Power Grid. But when we're talking about the modern power system, not the earlier power system, then you can see here, as we already discussed, if there is a two-way communication between the two, then the system will be more reliable and efficient, and output will be more. And you can see here the consumer, energy provider, transmission, distribution, and consumer communication devices, they all are communicating each other to make the system more reliable and efficient. So when we're talking about the characteristic of modern power system, so we can see the wide geographical spread. As we know that in India, I will show you in the different slide. how this whole India is divided into how many regions and zones, and previous how many grids we have, and now uh, how many grids we are running right now. So, and large number of interconnection, how these transmission lines are flowing from one part to another, and what is its total length, we will see. And secondly, we can see the rapid growth of demand in the electricity. This is because we already know that our standard of living is already increasing. Previously we don't have an AC in my house only, but yeah, these days we have installed two AC. So resources are not increasing, but the standard of life is increasing, and everyone need a proper life. And if they need a proper life, their demand is increasing, and if their lifestyle is increasing, obviously the electricity demand is going up, but the resources, the land is same. So we can say that the power system component are being operated closer to their design limit. Everything is running at closer to the design limit, and that's why we are more concentrating toward the high penetration of the renewable energy resources, and also we are going toward the competitive electricity market. So these are some measurement and and sensing elements, and you can say equipment that play a backbone of the smart grid. And we see that these days the smart meters and advanced in metering infrastructure are we are putting all over. I think in South we have already installed smart meters, and we are in India, in UP also. One project is going under the supervision, I think, with UPPCL and IT Kanpur. They are working in this advanced metering infrastructure, and we can see these all, why we are doing these all things, so that we can get the real time measurement, and whatever we can avoid the congestion, we can assess the market what is going on, we can make the demand side management. So that's why we are working right now toward and we can also say what are the losses going on in the distribution side. So also, synchrophasor technology as well as the PMUs are playing important role, which are going to provide a time synchronized measurement from a distant location and giving a data toward to the center. And wide area monitoring, you already all guys know what is a wide area monitoring protection and control system. So there are some communication protocols which we have to understand, and we are not going into a detail, just I'm going in trying to give an overview. And if we are talking about the SCADA, if we are talking about the smart meters and how they are talking from the smart home. Smart home means your home if there is a smart meter, and how this smart meter are communicating to the monitoring station. They can come either through a global system of mobile communication, and they can come through internet or ethernet, wi-fi, wireless network. And you can as I have tried to shown you through figures which are mentioned here. And these smart meters that can be used, metering of the data measurement system, as well as integrated integration of MD. MS means a meter data management system. I will try to explain you in the last slide and in a few slide after that what is a SCADA system and how you are going to monitor your REC Sonbad sitting at one place. And IT Jammu is working on that, as IT Kanpur is already have floated the tender, and they have one smart city building only, where three floors building where they are sitting, and they are watching all over the campus how the things are going on. So IT Jammu, as I'm the student of IT Kanpur, and my senior professors, as I have when I was there and I was watching all this thing, I was also involved. So I have also tried to implement all this thing in IT Jammu, and we are working in the SCADA system, and the whole campus of IT Jammu is starting from the initial stage to the final stage will be monitored from one control room. So these are some advanced technology. I'm not going into a detail, they are well available in the internet and sources. As we are talking about the communication, there are some hardware part also which are modified, like cables, like आजकल कहते हैं ना advanced storage devices like fuel cells, then advanced generation technology, then conductors as is shown in the figures. So they also play an important role when we are talking about the smart grid connections. So this is an overview of the smart grid network, and you can see that we have used the three different color arrows. And when we're talking about the red one, it is an intelligent ICT network, how it is communicating and how it is connecting. And then we have a navy blue and sky blue, and you can see in the sky blue there is a unidirectional only one directional flow, but in the navy blue there are the bidirectional also. And when we are talking about the bidirectional, you can see there are three bidirectional. And you can also see that there are some wind farm and solar which farm which are connected directly to the transmission, and there are some wind farm and solar which are directly connected to the rooftop. As you already know that recently Prime Minister Narendra Modi has inaugurated I think 750 megawatt solar uh, plant in Riva, MP. So huge big plant can be directly connected to the transmission system, but the roof plant which are connected to your rooftop, connected to your small college, connected to your small buildings like office, they can be connected to the distribution network. And you can see the bi-directional flow. When we are talking about the energy storage, and it is connected to distribution, that we have a UPS system like in IIT Jammu. We have 400 kilowatt UPS system connected to our IIT Jammu network, and we are taking care of all the thing. If the supplies goes out, at least all the minimum requirement we can fulfill. So similarly, the electrical vehicle, they are also bi-directional. It is well known. And the microgrid. And when we see a microgrid, you can see a distribution network you can keep in the one platform, and the small microgrid you can keep into another platform, and how you are going to interconnect these two. So, this is an overall SCADA system. And when we're talking the SCADA system, everyone know what is a SCADA, supervisory control of data acquisition system. And this is a diagram that I have shown you. Right now we are working in IT Jammu network, and we are trying to control some of the feeders. Means when we're talking about the feeders, means we are talking both the substation right now we have in IT Jammu, as well as some of the distribution panels which are located at different buildings. And all the whole building, as well all the substation will be taken care of the monitoring and control. uh, Let me give you an example. Suppose we are right now, I am running a machine lab as it is under me, and suddenly my lab assistant forget to close some machine, and XYZ load was running, and suddenly it comes to know the experiment is, time is already over, and still the loads are going on. So the guy who was sitting in the control panel, he can shut down that whole floor. So it is well known that how you are going to control the things sitting at the one room. And let me tell you one thing, the things which monitoring is okay, you can do the monitoring. How you are going to do the monitoring, you have ammeters, voltmeters, every meters available in your distribution panels. But when we're talking about the controlling, so in the controlling means, until unless your substation, unless your distribution box panels which are located in the building, they are SCADA compatible. Means the circuit breakers, the relays which were located in the substation, in the distribution box, if they are not motorized, you cannot do the controlling part. So when you are planning to have an SCADA system in any campus like REC Sonbhat, please work on initially that whatever panels, whatever things you are purchasing, it is a SCADA compatible. Otherwise it will not work. So now coming to the few challenges and R&D that can be taken into a care when you are planning to do in the microgrid. So few challenges are voltage stabilization, power management, PQ management. This is not a real and reactive power management, it is a power quality management. Then the protection, grid integration, stability issue, and islanded protection. These are the some challenges that we are facing in the microgrid research that we are working on. And when we're talking about the R&D, research and development, that we can be work, first we have to see the microgrid architecture. Microgrid architecture, that means what you need in your microgrid. Means, see, when we're talking about the microgrid, you can include supercapacitor, SOFC, solid oxide fuel cell, then you can include electric vehicle, then you can include wind, then you can include solar, then you can include DG. So these are all then your grid. These are all part of, microgrid. So what is your architecture, what you want in that? Solar, wind only, then solar, DG, and battery storage, then grid only. So first of all, decide what are the resources you want, according to the locality, according to the area. Then what is your plan? You are going to work in AC, DC, microgrid both, or you want to work in AC or in DC, or the combination of both? Then converter topology. Okay, if you don't want to take care of the resources and everything is available to you, then if you are guys from the power electronics and you are the guys from the electrical side, then you can see how you are going to change the topology of the converter so that the things can work in the microgrid. Then control architecture. When we're talking about the control architecture, the things are there in the grid, then how you are going to control the things. And what is your architecture means, you have to work on the control side only. Then MPPT scheme, everyone knows. Then adaptive and fast production scheme, islander detection and management scheme, then smart converter and inverters. As you know that a solar and battery, all these are DC, and if you want to convert into an AC, then you need some power electronics devices. So how much these power electronic devices are smarter and giving less harmonics into the system, integrating less harmonics into a grid, then virtual energy generation, then micro energy management system. So these are the some you can pick one of them, and you can work and do some research. So not going in more detail, coming to the part of the Indian power sector right now, what we have starting from the central government to the state and the rural regulatory. So I think everyone know what is NTPC, everyone know what is CEA, everyone know what is NPTI, CPRI. So these are the a central a small flowchart that I want to show you, and how our electrical Indian power sector are working right now in India, starting from the central to the state government, from the rural electrification, from the trading corporation, from the IPPs and regulatory SERC, etc., power exchanges. So these are some sectors that in which in whole power sector of India is divided. So, and this is an overall status right now in India. This is a data taken from February to March 2019, and you can see that the REC installed capacity and total installed capacity is shown here. And we can see that when we're talking about the PV, you can see I have mentioned here in the blue, purple, that 100 gigawatt by 2022. The Modi ji target is we have to install an 100 gigawatt power supply from the solar, 60% rooftop, I think 40% on land. So this is their plan, and this data, let me tell you, is taken from the Ministry of Renewable and Resources Energy, March 2019, and Central Electricity Authority, as I already mentioned you in the last, that is called as CEA. And you will be very surprised then when we're talking about the how the power is generating, and you can see that private sector is giving us 46% of the whole power supply, and the central government is agency is giving 24%, and rest is coming from the states. So this is a power situation that we never, as I already told you, what are the that every equipment is running on their maximum limit, and the energy deficit, the demand in between this war in between March 2019 to April 2018 was 12,134 mega unit, and we met only 12,03567 mega unit. It means we were in the deficit. Similarly, peak demand, we were in the deficit. Please forgive me. The data for the per capita consumption electricity was long old. I have not received the recent data, but in 2015-16 it was 1075 kilowatt hour per year. But obviously from in 5 years the data has been changed drastically. So this is, what I was trying to say when I have mentioned the interconnection of network in India, and you can see the whole India previously was divided into a five region. And in December 2013, when the southern grids comes in touch with western and eastern grid, then our nation is known as one nation, one grid, and one frequency. So previously we have five grids, but in December 2003, when the southern grids comes in contact with our rest of the grid, then our nation become one nation, one frequency, and one grid. So, and you can see how these regions, how much renewable energy resources and how much total generation is coming from each region. It was given in this table, as well as I told you, when we're talking about the network and how the transmission lines are running from one place to another and how much kilometer they are covering. And you can see it is a data till 28 Feb 2019, and I have not included 1200 kV transmission line because only one commercial line is running between Varanga and Wardha in Mumbai. So it was not included here in this table. But yes, in the rest of the line, you can see when we're talking about 765 kVA line in India, it is running 40,873 kilometer, and 400 kVA line it is running 1,79,269 kilometers. So this is an overall structure of the transmission line and the reason wise renewable and total generation. And these are some initiative which was taken by the central government to towards the smart grid and renewable energy resources. And you can see from 2010 it was started. And in every forum, every mission, they have their own website. And if you want to know what objective and what are the plans the government is planning under these forums, you can go through that. And in 2010 we have Indian Smart Grid Task Force. Then we have in 2010 again, then we have a forum. Then in National Smart Grid Mission in 2015, then expert panel on smart transmission grid by Power Grid was again mentioned in 2010. So these are some projects which was initiated in with initially initiated in the smart grid pilot project. And IT Kanpur was the first academic and research institute who got this project. And it right now also they are working in the smart city project. And you can see these are the objective, what they are planning and what they have already completed. So this is they are some small objective and the objective that they have already succeeded. But yes, if you want to go in more detail, you can directly type www.itk.ac.in/smart city. You can get the the overall website of the smart city project of IT Kanpur, and what are the objective and what are they have already implemented and what are remaining they are working on. You can see from there. So I'm not going into more detail. So now when we're talking about the smart city grid, sorry, project which was funded by DST initially, and it was covered by IT Delhi, IT Roorkee, IT Kharagpur, IT Bombay, and IT Kharagpur. And these days, number of smart city and smart grid projects are running. They are some initial projects which was taken care. And when we're talking about the DST in collaboration with the international agencies, so these three IITs are right now working. IT Kharagpur is working with in UK India Clean Energy Research Institute, and then IT Bombay again working with United Kingdom Center for Education and Research in Clean Energy. But IT Kanpur is working, with United States. United IT Kanpur is working with the United States, and which is the project of approximately 200 crores. And in this more than 8 IITs and uh, from India, and more than 8 to 9 private and public sector. It means that from India team we have around 15 members, and the leading institute is IT Kanpur. And similarly, from the Washington state, when we're talking about the US, the Washington State University, Denver, is a leading institute. And from there also, there are a number of institutes and some of the industries which are participating in this project. So these are the some, government of India new initiative that was taken recently, and you can see the color. They have initiated Renewable Energy Management Center. But what are their objective? Their objective is renewable forecasting, SCADA for RE generation, scheduling of RE. Similarly, battery energy storage system. What are their objective? Testing of different battery technology at grid level. So there are a number of initiative which was taken by the Indian government. As you already know, green energy corridor, then wide area monitoring protection and control system, demand response pilots, and these days everyone knows. I think you also have one expert lecture from Thapar University, Professor Dr. Mukesh Singh from the electric vehicle. So recent government initiated toward the promotion of the electrical vehicles also. So the government of India new initiative, we can see that the National Load Dispatch Center is also divided into some sectors: Northern Region Load Dispatch Center, Western Region Load Dispatch Center, Southern Region Load Dispatch Center, and they are the number of states which are taking care, and they are coordinating to the power sectors. Now, I'm coming point to the renewable energy resources. I have already given you a data from February, March 2019. So again, I have given you a recent data that is also coming from the MNRE till October 31st, October 2019. What is the wind energy, solar energy, biomass, and small hydropower? So right now we are concentrating toward the solar energy, and when we are talking about the solar, we can work in three different areas. But one is thermal conversion, then is photovoltaic conversion, then biological conversion. So as an electrical engineer, we will concentrate right now toward the photovoltaic conversion, where we can see and how the electricity can be taken out from the sun radiation. So this is an a largest grid connector solar rooftop plant. My friend, this is not a on land. This is a rooftop which is grid connected, largest grid connector rooftop solar power plant, which is a 7.52 megawatt Dera Basi, Amritsar, Punjab, which are connected to the grid. And these are some pictures how it is connected, and these are transformer, substation, and the battery storage that they have. So when we're talking about the solar, how you're going to design and what you are required, I think most of you members already know. First, we have to decide the sizing of solar module, sizing of inverter, sizing of suitable switch gears, selection of MB transformer, selecting a suitable AC DC cable, selecting a suitable protection of lightning induced surges. So when we're talking about the installation of the PV after the selection, how, where, and how we can install, so there are six different, installation diversification. First of all, the utility scale plant. Recently, Modi ji has inaugurated 750 megawatt. Then we can, plant solar PV on a water surface. Please correct me if I am wrong. I think, as per my experience, the first PV which was installed over the canal of the river, which is in Gandhinagar, of about 1 megawatt, we have visited in 2016. The whole 1 megawatt solar plant was, installed over the canal of the river. Means niche se river was flowing, and on the above of that canal of the river, they have planted installed these solar panels, and it was generating approximately 1 megawatt, which was connected to the grid. And then we have a commercial rooftop. As we know that every industry, and IT Kanpur also, in their academic section, academic blocks, they have installed solar. Then we are talking about the mountain area. As we are in the Jammu, we can select some mountain area which will give more reliable radiation. We can hit the solar and generate the electricity. We can select. Then we have floating system. Means we can also put our solar panels on the river, and these panel can float, and we can take this connection and coming back to our distribution box. And obviously, some of my friends sitting in front of me also have installed a solar panel at their residence, so it is a residential part. So these are the major components. So solar panel, mounting modules, combiner box, inverter, transformer, switchgear, and back to the grid. So as already discussed, when we are how where and how we can install the solar panel. So solar module, when we're talking about the India, we have to take care that we are in an Asian country, and generally we use a polycrystalline modules, and for the power range of 5 to 360 watt, and the efficiency is around 13 to 17. And America is using a thin film, and European countries are using monocrystalline. But when we decided our module, then we have to decide the infrastructure, where we have to install. See, there are some, we can install in the land, we can install on the rooftop, we can install on the rooftop which is, have certain slopes. So the mounting structure is also an important, and at a certain angle, and we have to do some homework related to that, how the radiation is coming, how and you can see there are some structures which are, motorized, and you can see the black, in the black color. This is a motorized structure, and in IIT Campus Solar Park, we have this motorized structure. As the radiation of the solar changing their direction, this structure also changing their direction and following the same path as the solar is changing their direction. So after that, you can see, after installing all these solar panels, then structure has been decided, then you have to do some connection, and these connection will come into a combiner box. And you can see where, below the combiner box, we have taken 30 solar panels which was connected, and how these are connected in series parallel, and then these series parallel connection are going into a combiner box with a green and black line, you can see. And from this combiner box, what this combiner box, see, you can see by you can visualize the picture also, and you can see the bullet points, what is the work of this combiner box. And from the combiner box, you are taking two wires, right? And these wires are going into a solar inverter. And when we're talking about the solar inverters, let me, my friend, solar inverters are coming in with a different category. And residential, as we know, our house load are generally come in between 1 to 5 kilowatt. So residential inverters are different, string inverters are different, central inverters are different, then container inverters are different, and they totally depend upon the capacity at where we want to locate. So my friend, when we're talking about, Modi ji inaugurated 750 megawatt, there we cannot install a residential inverter. Obviously they have used the container inverters where the capacity is much higher in megawatts. And as when we're talking about the inverter technology, this ABB, Schneider Electrical, Siemens, and L&T, they are working a lot how we are going to improve these inverter, features in such a way so that the system will become compact and they give more features. And you can see, before 2017, I'm not going to give everything in detail, as you all guys are from electrical engineer. You can see pre 2017 the inverter was, the feature that they have 400 VAC output, kVA 80, single MPPT tracker was there, then 5 kVA, then 4 MPPT. Then in 2018 the specification changed, then 2019 again the specification changed, and still they are working how to, have a compact and smart inverters in our market. So these are some challenges, and some of the challenges we have already discussed about the microgrid. But when we're talking about the renewable energy generation, we already know that solar and wind, they are intermittent and uncertainty is there. So we need accurate forecast and power balancing. Then voltage and frequency control. Many of these sources do not have reactive power generation. As the best example, you can take a solar. Then a sudden generation losses can lead to a system instability, loss of inertia. As example, sudden big plant was connected in the grid, and suddenly it was out due to uncertainty where solar and wind are there. Then there may be a chance of instability. Then power quality issues, harmonics. If there are power electronic devices they are installed, obviously there will be some harmonic which will be, inserted into a grid. Then under the that we have to take care according to the IEEE and IEC standard we have to follow. Then power management and maximum power tracking and require proper converters and there are some challenges. I'm not going again into this detail that we have a SCADA, EMS, then thermal storage, microgrid challenging. Now coming to the wind part. So when we're talking about how we are going to integrate the wind into a grid, we can see uh, uh, why we are promoting renewable energy. You can visualize from this picture as a demand of the electricity is increasing, but yes, the natural resources, uh, they fuel, coal and nuclear, this uranium and everything is going down. Obviously population is increasing. As the best example you can take from New Delhi, as Faridabad power plant is located in middle of the city. As well as that's why we are promoting renewable energy resources, so that we can take care of these negative uh, objectives to be declining in the part, like fuel cell the fuel, if one day will come that they may be in the deficit. So this is why we are promoting renewable energy resources. But obviously when all these are interconnected, we have to take care that the thing should be and secure and optimal. Optimal means you can see one bulb is holding a dollar sign. So for that we have done some research in IT Kanpur in my research work, that we have proposed unit commitment with wind power uncertainty. And in this wind power uncertainty we have done nothing. What we have done, we have developed one new clustering technique. But before developing a new clustering technique, we should have some forecasted data of the wind. So forecasted data of the wind has been taken from the NRE website, and then we have taken some prediction error. Then we have generated some scenarios using Latin hypercube Klossky decomposition method, not Monte Carlo. Then we have reduced these scenarios uh, uh, and do some analysis according to the probability distribution. Then as most of my friends sitting here know what is a particle sum optimization. Obviously everything is available, data is ready, then we have to use some optimization technique. So we have used particle sum optimization, but yes, my friend, we have done some modification and renamed that particle sum optimization as a weighted improved crazy particle sum optimization. And instead of using a penalty function method, we have used pseudo inspired algorithm, where we are accelerating this optimization process. And after arranging all these coding things, we have to insert a data. And when we're talking insert a data, the system of the test is 10 thermal unit, 2 hydro unit, 1 pump storage unit, and 1 large scale wind farm. So when we're talking about the pump storage unit, as all of my friends know, what is a pump storage unit? Pump storage unit play a same role as a battery storage plays, because when there is a peak load, then our battery, what does battery do? The battery will discharge and try to supply the load. But yeah, when there is a valley load, you know, then what will the battery do? It will take a supply from the grid or supply from the network, and it will again charge. Similarly in the pump storage plant, there is one hydro plant which is known as, which can be called as a pump storage. But in the hydro power plant, what we do, we only generate electricity. And how it's generated, we have two reservoir, one on the top and one on the bottom, and through the penstock the water comes from the reservoir, and it will hit the vertical turbine. And as we know, the vertical turbine will move, then obviously RYB will come out and it will given to the transformer and it will transmit it. But in the pump storage plant, the same turbine, same generator will act as a generator and will act as a motor. So uh, uh, there is a dual mode there here. And when there is a peak load, this plant will work as a generating plant, and it will take a water from the reservoir and it will generate electricity. But when there is a valley load, what it will do, it will pump up the water from the lower reservoir to the upper reservoir, and it will act as a motor. So sometime it will act as a generator, means source. Sometime it will act act like a motor, like load. So this is a role of pump store power plant. So here we can see we have taken the wind forecasted data and prediction error. Then through Latin hyper, I told you, Latin hypercube sampling with Klotsky decomposition, we have generated 1,000 scenarios. You can see in the figure, we have created a band in the, square dots. You can see these are the forecast. This line is a forecasted data, and star and triangular pink and star line is a upper bound and lower bound, and in between we have generated 1,000 scenarios. And these 1,000 scenarios has been reduced by three different techniques which are already available into a literature, and one technique proposed by us. So what was our plan? This is a proposed technique. It is already published in paper. You can go through that. If you want to work in this, you are most welcome. So now, coming back to the scenario analysis, see, we have generated 1,000 scenarios, and these 1,000 scenarios has been reduced to X number of scenarios by using three well available techniques in literature and one proposed by us. So what we have to take into a consideration, we have to take into a consideration that system should be secure, reliable, because wind is there, which is uncertain, and system should be operation. The operational cost of the system should also be optimal, because there is a thermal, there is a hydro, there is a pump storage, and there is a wind. So using this system security and system operation cost, we have generated a scenario index, which is given equation number 3. And from there you can see omega s is a probability. And what is which probability? Probability of the scenario. Of which scenario? Wind scenario. So this is an overall equation of the unit commitment when you are planning. But we have inserted omega s, which is a probability of the wind scenario, and these are some these are some constraint. And the equation number 5 is known as a balance equation and balance constant. And my friend, you can see in the left side as well as in the right hand side. In the left side you have four section. One is a generation from thermal unit, PITS. One is from PSKT, means generation from hydropower plant. And then we have generation from wind. TS means different scenarios. Then we have PGT, generation from pump storage, which is equal to, these are all generation, which is equal to, I think everyone knows, which is equal to load, which is equal to losses. And here comes the one role which is called PPT. As I told you, pump storage plant will act as a both generation and uh, generation side and load side. Sometimes it will pump water and act as a motor. When it is acting as a motor, then that's why it is coming into the right hand side of this equation. So there are some time period when it is acting as a generator and motor. We will show you in the graph. So this is a balance equation, and my friend, there are some reserve ramp up rate, ramp down rate, reserve constant rate. Because every when we're doing a unit commitment, we have to take some reserve of around 10%. Generally, whatever we have noticed, that the reserve, we have to set up some reserve around 10% of the total load. And when we're talking of the ramp rate, because when we're talking about the ramp up and down, so I will try to give you a small what is, I think most of you know, but if someone don't know, I will tell you that ramp up means if the generator is running at 100 megawatt and suddenly the load is increased to X, suppose. So you cannot run that 100 megawatt directly to the 500 megawatt. It cannot jump 400 megawatt at a certain time period because of its inertia, because of its design. So there are certain ramp up limit. If generator is running at 100 megawatt, it can only jump to 300 megawatt. So ramp up rate is 200 megawatt. It is a percentage of that maximum rated capacity of the generator. Generally we have 60 to 70%. So similarly, there are some constraints which are mentioned in equation number 6 and 7. Now we will coming back to proposed approach, which is named as weighted improved crazy particle absorption optimization. So my friends, the bold colored, which is given in red font. These are some modification that we have done. Generally, when we are talking about the particle sum optimization, we have inertia weight, we have acceleration coefficient, and inertia weight generally we take zero point 0.4 to zero point 0.9, and the acceleration coefficient generally we take 2 to 0.2. And some of the paper we have seen that the acceleration coefficient increases linearly as the iteration goes on. But here we have done some modification. What we have done, we have randomized the acceleration coefficient as well as acceleration coefficient with respect to the minimum value which was given in equation number 9 and 10, as well as we have also included the p vast. Means if the particles are trying to move toward the vast, and they can that data should also be stored, so that we try to modify the next particle in such a way that they should not go toward the worst condition. They should bend toward the p best or g best. So this is a pseudocode algorithm that we have proposed, and it is well known. A number of paper I have published in this with different GFTS, GSA and BAT algorithm, then PSO. So here we have not used penalty function method. Here we have used iterative modification of the particles. Every time if you see that the particles are diverting, then you will iteratively try to modify that, and then check the tolerance. Back to back you can see PG gap. This is the tolerance we are checking, and if it is less than, then we can stop, and this will go to the PSO part. So if everything is done, every data is done, reduction techniques done, probability taken care, PSO ready, acceleration process ready, then what is your what is your data, what is your system? So let me tell you the system that we have planned with 10 thermal unit, 2 hydro, 1 pump storage, and 1 wind farm, which was previously not available in the literature. So how we are going to know that whatever we have proposed is, you know, is reliable, is good? So what we have planned, we have planned to first check with the 10 thermal unit, because it is the data and the results are well available, and number of papers are published in IEEE and elsewhere. So we have taken the 10 thermal unit as a benchmark, and then after getting this result and compared with the previous, then we have taken our system and do the analysis with some different reduction technique that we reported in the literature, and with us technique that we have proposed. So see, you can see the cost comparison, and you can find that proposed weighted improved kg particle optimization technique give best result in the form, not only the cost but also the quality based solution is 100%. The rest you can see BCPSO, ICPSO, PSO is 99.95. And then we have talking about the percentage deviation from the best, how it is diverting. It is diverting less than 1%. So these are the scenarios that was generated from 1000 to 10, and with well known technique which was available in literature, k mean, hierarchical, and backward. And you can see these are the probability that we have got, and these 10 scenarios are sent to our system, what we have modeled. And see, these are the scenarios. This was a band, upper band, lower band, and these are the 10 scenario which we have picked out of 1000 scenario. And you can see in figure number 8, figure number A and figure number B, was the technique was taken care by the k mean and hierarchical. And my friend, you can see the upper reserve constraint is violating. Means the generation should be higher than the load, but here generation is less than the load. Means you can see the black line which was just below the mountain figure. You can see just below that black line and 10 different color line, and some of the colorful line are above the black line, which is not permitted. This is a zoom picture that we have taken from this curve, upper curve. So it is violating the upper reserve constraint. Similarly, figure number B, the black line again the colorful line are violating the constant and violating at uh, 2 2 hours, which is 14 hour and 19 hour. But my friend, we can see the figure number C, which is a backward reduction technique. All the 10 scenarios in the system are lying below the backline. It means that k-mean and hierarchical are not, proposed technique are not good for the system. They cannot be considered when we are planning our system with uncertainty of the wind. But yeah, backward reduction technique can be taken into a consideration because they are, giving good solution. We cannot say they are giving optimum or not, because every technique have their different optimum. But yeah, they are satisfying all the constraint of the network and giving the reliable solution. So these are some, curve that we have achieved. uh, these curve, these, triangular, star and diamond, they are the wind flow which we have achieved from k-mean, hierarchical and backward. And you can see, my friend, the pump storage unit, uh, sometime it is pumping at our number, रात के 11 1 बजे देखिए पंपिंग हो रही है, 2 बजे पंपिंग हो रही है, 3 बजे पंपिंग हो रही है, क्योंकि रात का लोड कम है तो वो पंपिंग कर रहा है। रात सुबह के 4 और सुबह के 5 बजे कोई ना पंपिंग हो रही है ना जनरेशन हो रहा है, लेकिन सुबह 6 बजे फिर पंपिंग हुई और फिर वी हैव अ न्यूट्रल। देन सडनली सी ऑफिस खुले होंगे, all the office has been open, all sub they all are active, then see this pump storage power plant started generating. You can see, my friend. Then again at around 2 to 3 hours we have a little bit of pumping, but pumping when we have backward action technique. Again we have at 3 o'clock pumping when there is a hierarchical and backward. But again शाम को 4 बजे 5 बजे 6 बजे पंपिंग हुआ। देन अगेन जनरेशन हुआ। जनरेशन कब हुआ? जब सारे ऑफिस बंद होकर के घर में आए, सारी चीजें चल रही हैं, रात के 11 12 बजे जब सो गए फिर पंपिंग हुई। सो दिस इज ऑप्टिमम रिजल्ट दैट वी हैव गॉट from these three techniques. And you can see the deterministic cost and stochastic model cost. So you can see, let me brief you what is a deterministic model and stochastic model. Deterministic model is a model which is set up taking care of only the forecasted data. We have not introduced any, uncertainty of the wind. And stochastic model is a model where we have taken care of the uncertainty of the wind. And my friend, you can see the stochastic model is much costlier than the deterministic model. Obviously, if you want a reliable solution, you have to pay more. So without ramp and with ramp, my friend, I already told you what is ramp rate. So first we have taken without ramp, we have considered कि ठीक है अगर जनरेटर 100 पे रन कर रहा है वो 500 पे भी चला जाएगा, तब कॉस्ट क्या होगी। लेकिन जनरेटर 100 पे चल रहा है and it will go to 500, it cannot go to 500 because there is a constant inertia and design. So we have considered both without and with. And you can see when there is a practical model you have taken, obviously the cost is increased as compared to the without ramp rate. So this is the result that we have got by our proposed technique. And the best thing of my our clustering technique is that there is no need to enter how many scenarios you want. It will automatically give you according to your need. And you can see again there are some mount valley curves, mountain type of curves, and curve number A, B and C. And curve number A and curve number B, these are the two curves which are taken from the our clustering technique without pump storage. And when the backward reduction technique previously giving all the good solution when pump storage was not introduced, but when pump storage was introduced, backward reduction technique also fails. You can see in figure number C. And because at 11th hour and 22nd hour, backward reduction technique violating the constant, because जनरेशन होना चाहिए था 1412 मेगावाट और जनरेशन हो रहा है 1402। सिमिलरली at 22 hours means at रात के 10 बजे जनरेशन होना चाहिए था 910 मेगावाट, सॉरी 910.9 मेगावाट, लेकिन जनरेशन हो रहा है 910। so upper reserve constant is violating. But you can see in figure number A, this is a clustering technique which was proposed with pump storage. See the curve, both are likely same. So you can see C and A, but here there is a violating, but here everything is under control. and the system is reliable. So what we can see, these are the some changes that we have found in the pump storage, how the pumping is done as a result, as compared to the technique which was reported in literature. So obviously we have done some new analysis, because somebody can ask why you have taken 25% of percentage error. So to justify, or you can say to answer them, we have also taken 20% prediction error, 30% prediction error in the paper. And you can see from the results, as the prediction error will go high, the cost will go high, because the band will increase and the uh, uncertainty will also increase a particular instant. So now I'm coming back to the conclusion, and when we're talking about the conclusion part, the proposed clustering technique is more reliable than other technique available in the literature. And obviously the stochastic model is $7,862 higher than obtained from the deterministic model. And let me tell you, this $7,862 is per day cost. And I also tell you, this is a per day cost. And you should also know that when I was in America for the postdoc and got an opportunity to work for 5 years, but I got an opportunity in IT Jammu, I was in back. So this where I was getting only $3,000 per month, and you can see we have saved $7,862 per day. So also you can see pump when you have introduced the pump storage power plant with stochastic model, you can see the cost reduced to 6,721. Means you have done nothing, you have just included one hydropower plant which is acting like a both pump storage and hydro, and this is reducing the cost to around I think 80 to 90% in between, with low risk of scheduling uncertainty of the wind. To my friend, we can say the solution enable a power system operator to plan the operation of the system under uncertainty of the wind power, which was connected to the grid. So the future scope, I have worked for 24 hours. You can work for 1 week and more. Uncertainty, I have taken scenario reduction technique. You can use uncertainty set and probabilistic constant. I have not I have not entered into electricity market, but yes, I have published one conference paper which was published in, I think, in Portugal, ISAP. I have written one paper with taking care of the price and bidding process also, but no general paper I have published in this area. Then multiplying multiple conflict objectives, such as SCUC, means security constraint unit computer problem, some fault, some contingency analysis, you can take care of that. Then fast technique, artificial approach you can use, gravitational search algorithm, bat algorithm, number of algorithms are coming these days. You can see how you can work. Then the same technique you can apply to our northern region grid, as we are from here, and you can take a data of the northern region grid and you can try to apply in this. So these days I have totally switched my research topic. That's why I have not published any research paper in optimization from last 2 years, because I have totally changed my topic from optimization and integration to solar and wind microgrid. And right now I am developing a microgrid testbed laboratory in IT Jammu, and we have already purchased an RTDS with of 2.25 crore. And now I'm planning to purchase some PMUs, controllers, amplifiers, as I have shown in this figure, so that we can set up a microgrid lab, testbed lab here, and we can do some real-time research. So this was all about our smart grid and a little bit of Indian power sector, then little bit of solar, then little bit of wind. Please, if you have any question, you can ask. Thank you so much.
So, participants, please ask question if you have.
Good morning, sir.
You can.
Good
Am I
morning. Good
audible?
morning.
Yeah,
Yes,
yeah.
sir.
Sorry, you're audible.
It was a
Yeah,
very
yeah.
informative session. Sir, you were talking about the you can apply it into the contingency analysis. So, sir, give
Yes,
me
yes.
some idea about that, how I can apply it in case of that.
See, when we are talking about the country, yeah, uh, Naranji, I'm audible.
Yes, sir, you are audible.
Hello. So, when we are talking about the contingency analysis, as we know that in the power system protection, there are some ranking method and some, if you want to, allow some contingency. So, which type of contingency you are talking about? We are talking about the generation should go out, the transmission line should go out, right? So, if we have a network, there are two possibility. See, load cannot go out. Load हमारा हमारा लोड आगे बढ़ ही रहा है, पीछे नहीं जा रहा है, बिकॉज आवर स्टैंडर्ड ऑफ लाइफ इज इंक्रीजिंग. सो एज पर माई एक्सपीरियंस दो ही चीजें आउट हो सकती हैं ड्यू टू फेलियर, या तो जनरेटर आउट हुआ या तो ट्रांसमिशन लाइन आउट हुआ. तो अगर जनरेटर है, 7-8 जनरेटर है, जस्ट एग्जांपल आई एम गिविंग टू यू, यू कैन प्लीज गो थ्रू द पावर सिस्टम प्रोटेक्शन syllabus where you can see how the contingency analysis has been done. So if the generator is, there are 7 generator and some number of transmission line, so you have to rank these in the priority basis, and then you can take one out and you can see what are the impact is going on into a system. So you're getting a point. Ranking
Yes.
of these things should be done. If you will rank which is more severe, according to that you can plan n-1 contingency, n-2 contingency into your system.
Okay, sir.
And I request you to please go through the course of the power system protection, and where you can see how the contingency analysis, security analysis is going. There are number of ways you can do that.
Okay, sir.
अनुप सर, मैं आपको ये बताना चाह रहा हूँ कि ये ऐश्वर्य नारायण जी एस एन सिंह के अंडर में ही पीएचडी कर रहे हैं, तो मुझे लगता है कि इसलिए आपसे इंटरेक्ट हो रहे
अच्छा,
होंगे।
वेरी गुड.
Yes,
अच्छा,
sir.
अच्छा. नहीं, नहीं, तो अगर ये एसएन सिंह सर के अंडर में पीएचडी कर रहे हैं तो यू कैन कॉन्टैक्ट मी डायरेक्टली. आप सिंह सर के पास तो मेरी बात होती रहती है. आप किसी से भी नंबर ले लीजिएगा, आईटी कानपुर में सबके पास है. इफ यू हैव एनी डाउट, यू आर मोस्ट वेलकम.
Okay, sir. Thank you, sir.
Okay. So, any other queries from any of the participant? You can write in chat box also, so that sir can read it and can give a reply. Okay. Okay, no. Dharmendra Singh, no. Okay, sir, I think there is no queries from the participants. So, thank you very much, sir, for this wonderful session and a very informative talk about the smart grid. So, hope our participants enjoy this session and get something to lead in their research work. And I think sir have also given us his contact number
So
or uh, email ID, so that student can write their queries to you, sir.
the members as well as the faculty members and the students who are sitting in front of me, if they have any assistance from my side, you all are most welcome. Thank you so much.
Okay, sir. Thank you, sir. Thank you very much, sir. So, participants, we will again connect at 12 a.m. So, next lecture by Professor Anand Kishore, sir, from MNIT, Allahabad.
पटेल सर, रिकॉर्डिंग स्टॉप कर दीजिए।